Magnetostatic fields. Here we know that electrostatic field. We already discussed electrostatic field. So electrostatic field is produced by static charges, static or stationary charges. Static or stationary charges. Suppose if the charges are moving, with constant velocity. This is important. The charges are moving with constant velocity. A static magnetic field is produced. That is, if the charges are moving, means current will generate. So the current will produce. Due to that current, a magnetic field is produced around the conductor. So when the charges are moving with constant velocity, static magnetic field is produced. That is, a magnetic field is produced by a constant current flow. Constant current flow, that is direct current. So here this is E field, so this is H field because of moving charges or because of constant current flow. So this is the analogous. We can expect some analogous or analogy between E and H. E, H. Similarly, we have epsilon, here we will have mu. We have B is equal to epsilon E. Here also we will have B is equal to mu H. So like this, some analogy exists where D is electric flux density, B is magnetic flux density. We will discuss this clearly. So like this we can expect some analogy between electric and magnetic fields. Similar to electrostatics, where we have discussed Coulomb's law and Gauss law for the analysis of electrostatic fields, here also two major laws governing magnetostatic fields. The first one is Biot-Savart's law, and the second one is Ampere's law. Or Ampere's circuit law. So generally this Ampere's circuit law is used in problems involving symmetrical current distributions. So we will discuss these two laws. The first one is Biot-Savart's law. So what is Biot-Savart's law saying is, suppose this is a conductor, some constant current flow I is there, suppose this is a small length of conductor dl. So this is due to this current distribution at a power point, I am indicating here magnetic field with this cross. At a power point, what is the magnetic field intensity? Suppose this is making an angle alpha, this is the distance r. So at that power point P, what is the magnetic field intensity? So this Biot-Savart's law says that the magnetic field intensity is directly proportional to product I dl, that is the product of current flow and length, small length dl, and inversely proportional to r square, and also directly proportional to sin alpha, that is where alpha is the angle between the conductor and the point of interest, line joining to the conductor to the point of interest. So the magnetic field intensity is directly proportional to the product of differential current element this total is called ideal. Ideal is called differential current element. Differential current element. Dl and the sign of angle alpha between the element and the line joining P to the element, and is inversely proportional to the square of the distance r between point to the element. So this dH proportionality constant, the dH is equal to k into ideal sin alpha by r square, where k is proportionality constant. Proportionality constant, and is given by k is equal to 1 by 4 pi. 1 by 4 pi. Therefore, dH is equal to 1 by 4 pi r square ideal sin alpha. Ideal sin alpha. So this also can be written as dH is equal to ideal cross AR bar by 4 pi r square, because this ideal cross A bar is nothing but ideal into magnitude 1 sin alpha. Sin alpha, where AR is a unit vector along this. So I can write dH as ideal cross AR bar by 4 pi r square. So like this I can define magnetic field intensity at a 4 point P. Suppose this is a conductor, the current flowing in this direction I. Here we will use right hand thumb rule. So this is the right hand thumb rule. Suppose this is that is the field direction is like this. Suppose this is a right hand thumb. So the direction in which the remaining fingers, if you hold the conductor, so this remaining fingers will give the direction of the magnetic field. So like this, in this direction. That is, this is a conductor, the field is like this. The current is flowing like this means. So around the conductor magnetic field exists. Around the conductor magnetic field exists. This is right hand thumb rule. Right hand thumb rule. The second law is Ampere's circuit law. So this is one of the important law. So suppose this is a closed path. Some current I is flowing in this closed path. I unclosed in this closed path is I. The statement of Ampere's law is, it states that the line integral of the tangential component, of H around a closed path is same as the net current enclosed by the path. So that is, suppose this is a closed path. So some I is flowing along this closed path. So due to this, some magnetic field will generate around this closed path. So if you integrate the line integral, that is the line integral of the closed path, H dot dl is nothing but I enclosed. I enclosed is given by the current itself. If you integrate the magnetic field, here the magnetic field because of I. magnetic field is generating because of I. So if you integrate that magnetic field, we will get I only. This is the end result. I is the nothing but end result of magnetic field. So integration over L H dot dl is I enclosed. This is Ampere's circuit law. So here also we can say that there is a relation between circuit theory and field theory. Integrated effect of H is nothing but I. We already discussed when we were discussing potential. Integrated effect of E is nothing but the potential V. So this I and V are end results. So this is Ampere's law. So if you apply Stokes theorem, by applying Stokes theorem relates line integrals to surface integrals. That is, integration over L H dot dl is also equal to integration over S del cross H ds by applying Stokes theorem. I enclosed is also can be written as integration over S j dot ds. If you equate these two, integration over S del cross H ds is equal to integration over S j ds, where j is current density. So implies del cross H is equal to j. So this is called that is del cross H. What is the meaning of curl? Curl is nothing but circulation. The circulation of the magnetic field is nothing but current density. So this is Maxwell's third equation. Static case. I am discussing here everything is static case. This is also in point form. Point form or differential form. This is the integral form. This is integral form of Maxwell's third equation. Del cross H is equal to J. Here del cross H is equal to J. That is not equal to 0. So magnetostatic field is not conservative. Magnetic field is always it is a circulating field. Whereas del cross E for static case is 0. We already discussed del cross E is equal to 0. That is conservative field. That is electric field is not a circulating field. Whereas del cross H is equal to J. That is not equal to 0. That is del cross H is J means it is a not conservative field. Therefore magnetostatic field is not conservative. That is, this is a circulating field. Magnetostatic field is not conservative. So this is one of the important statement. So like this we derived third Maxwell's equations. So from electrostatic fields we derived two Maxwell's equations. Here also from magnetostatics we will derive two Maxwell's equations. This is the first Maxwell's equation third Maxwell's equation in magnetostatics case. Del cross H is equal to J. So there is one more Maxwell's equations we have to derive. The next topic is magnetic flux density. Magnetic flux density. So this is similar to electric flux density we discussed. That is the field lines of electric flux. Similarly here field lines of magnetic flux. So the magnetic flux density, this is indicated with symbol B. It is given by B is equal to mu naught H, or in general B is equal to mu H. Here we are considering free space. That's why I have written mu naught, where mu naught is a constant known as the permittivity. Mu naught is a constant known as permeability. Not permittivity, it's permeability. permeability of free space. If you compare this equation with electrostatic field, electric flux density is given by epsilon naught E. So this is a magnetic field is analogous to electric field only, where E naught is permittivity. So here mu naught is a constant known as the permeability of a free space. The value is given by, which is a constant, 4 pi into 10 power minus 7 Henry per meter. So this is a unit of mu naught. So we know that electric flux density is given by integration over S d dot ds. So if you apply the analogy also, here magnetic flux, this is magnetic flux, psi, magnetic flux is given by integration over S b dot ds, b dot ds. So magnetic flux. One more thing here, suppose if you consider a magnetic bar, so a magnetic bar consists of north and south poles. North and south poles. So if you draw the field lines always from north pole to south pole. North pole to south pole. So like this. The field lines of a magnetic material. So the fields are like this, leaving from north pole and ending towards south pole. The field lines are like this. That is, magnetic flux lines always close upon themselves. Magnetic flux lines always close upon themselves. Always upon themselves. Whereas if you consider electric field, so this is plus, so leaving plus charge. Minus means towards charge. Suppose you consider dipole leaving from plus and ending towards minus. But here this is a different case for magnetic field. Suppose if you consider magnetic bar, the magnetic flux lines always close upon themselves, because the reason is, this is due to the fact that it is not possible to have isolated magnetic poles or magnetic charges. So this is the reason, because it is not possible to have isolated magnetic poles, that is like north pole, only south pole, like this. It is not possible to isolate these two. Whereas if you consider electric fields, plus charges we can separate. Similarly, minus charges also we can separate and we can combine. That is, we can consider dipole also. Here, if you consider a magnetic bar, it has north and south poles. So it is not possible to isolate the north and south poles. So that's why the magnetic flux lines always close upon themselves. That is, even though if you suppose you consider a magnetic pole like this, and you are dividing into two parts, then what happens is, this becomes another magnetic bar, even though here it is again there will be north and south poles. Even if you cut this into two parts, again you will get a north south pole like that. So that's why isolation of magnetic poles or magnetic charges is not possible. So that is, I am considering a magnetic bar like this, having north and south poles. I am dividing into two. Again it becomes dividing into two parts. Again it is north and south pole, north and south pole. Again if you divide into two parts, again this is a north south, NS and north south poles, like this. If you divide like this. So that is, isolation of magnetic poles is not possible. Suppose I am considering a closed surface. This is a closed surface. Closed surface. I place a magnetic bar here, magnetic bar here. Then what happens? The field lines are always closed upon themselves. Close upon themselves itself, on the magnetic bar itself. Then what is the flux living through the surface? That is obviously zero. Because of magnetic bars, the flux living through the closed surface is zero. Because what is the reason? The reason is the magnetic flux lines close upon themselves. So there is no flux diverging from the magnetic bar. Therefore, we can say that total flux through a closed surface in a magnetic field must be zero. That implies psi is equal to 0, magnetic flux. That implies integration over S B dot ds is equal to 0. Integration over S B dot ds is equal to 0. But by using divergence theorem, we can write that integration over S B dot ds closed surface is nothing but integration over volume del dot B dV. So that implies integration over V del dot B dV is equal to 0. Implies del dot B is equal to 0. Del dot B is equal to 0. So this is fourth equation of Maxwell. This is fourth Maxwell's equation for static case. This is fourth Maxwell's equation, static case. So this is in point form or differential form. Point form or differential form. So this is that is equal to 0. This is integral form. The entire equation is integral form. So what is the physical meaning of this del dot B is equal to 0? That is the diverging of magnetic flux density is 0. So the diverging capability of magnetic flux density is 0 for static case. So this is our fourth Maxwell's equation. So we derived all four Maxwell's equations for static case with this final equation del dot B is equal to 0. So this equation is very, very important. So this means magnetic field lines are not diverging. They don't have the capability of diverging. Now we can summarize the Maxwell's equations for static case. So Maxwell's equations for static EM fields. So here I am writing point form or differential form. Here integral form and remarks. The first one is del dot D is equal to rho V. Del dot D is equal to rho V. So this is a divergence. It is del dot D is equal to rho V. What is the integral form? whenever is a divergence means divergence always relates surface integrals to volume integrals. So integration over surface integral d dot ds is equal to integration over v rho v dv. Rho v dv. So this is the integral form. So what is the remarks is this is derived basically from Gauss law. So the first Maxwell's equation is derived from Gauss law. So the second Maxwell's equation is del cross E is equal to 0. Del cross E is equal to 0. That is the electric field is non-conservative. So here curl always relates line integrals to surface integrals. That is integration over closed line E dot dl is equal to 0. E dot dl is equal to 0. This is the integral form of second Maxwell's equation. So what is the remark? We can say that non-conservativeness of electric field. Non-conservativeness of electric field. Sorry, del cross E is equal to 0 means conservative one. So conservativeness of electric field. Conservativeness of electric field. That is the circulation of the electric field is 0 means it is a conservative field. So this is conservativeness of electric field. Third one is we derived from magnetostatics is magnetostatic del cross H is equal to J. So this is integration over L H dot dl is equal to integration over S J dot ds. J dot ds. So closed line open surface. So this is basically derived from Ampere's law. Basically derived from Ampere's law. The fourth Maxwell's equation is del dot B is equal to 0. Del dot B is equal to 0. That is integration over S B dot S is equal to 0. So remark is non-existence of magnetic charges or magnetic poles. So this is also known as Gauss law for magnetic fields. Gauss law for magnetic fields. So this is a summary of Maxwell's equations. These are the four Maxwell's equations, very important. So in the examination we may expect to direct which of the following is a Maxwell's equation. So they may give any one. So either it may be in differential form or integral form. So you have to remember the two things. This is very simple. No need to remember also. Just if you follow, divergence relates closed surface to volume integrals, whereas curl relates closed lines to surface integrals. So if you remember these things, del dot D is equal to V, so easily you can convert into integral form.